Good evening all of you. Welcome to ACE Online. Now today we are going to see an important concepts in transformer and some questions analysis regarding RRB JE examination. Okay. Now first I'm choosing here mainly construction topic today. So I will give some important points in this construction of transformer and then we go to some important questions. Okay. However, we are getting questions in RRB JE. So most of the questions in RRB JE are almost basic level. So when compared to other competitive examinations, easily you can able to answer. Okay. So let's see some important points regarding construction first, and then we go to questions in transformer. Now, if you talk in construction of transformer, which topics are important? Construction. So first of all, what are the important parts we have in that? So mainly, in examination point of view, two parts are important. One is transformer core and transformer winding. But rather than this, we have so many parts in transformer other than this. What are the other parts of transformer we have? First of all, core and winding we cannot see directly. It is not visible for us. So if you see the transformers outside, what is visible for us directly? Tank is visible, transformer tank. So mainly we have to discuss here two parts. First one is transformer core and transformer winding. So these two are the important parts for examination point of view, and other than this we are also getting some questions in other parts of transformer, but mainly these two, transformer core, transformer winding. But if you see outside directly, tank visible for us, tank, and this core and winding immersed in the tank, and the tank is filled with completely transformer oil we call. And what is the purpose of the transformer oil? So if you see, this is the transformer core, and transformer winding. Transformer winding, and this is completely placed in a tank. This is completely placed in a transformer tank, and this tank is filled with transformer oil completely like this. This is transformer oil. And what is the purpose of this transformer oil here? So we call mineral oil or transformer oil, we call it is one of the mineral oil. Now why we use, or what is the purpose of transformer oil in transformer is it provides cooling and insulation. It provides cooling and insulation to transformer. Generally transformer core and transformer windings gets heated up whenever they are supplying loads. So due to current in the winding, copper wires heated up, and due to voltage we applied, this core heated up, because mainly two losses we have, iron loss and copper loss. Iron loss depends on the voltage we applied to transformer. If voltage increases, iron loss also increases. And what is the approximate relation between iron loss and voltage variation? Whenever voltages are changing or varying, what is the relation? How iron loss will change with respect to the voltage? The relation is approximately iron loss varying as square of the supply voltage. Approximately it will vary like a square of supply voltage. If little bit voltage increase, so much increase in iron loss will be there. So these questions also important we have in previous some of the examinations in RRB JE, like when voltage is 2% applied, how much iron loss will be there? How much iron loss with respect to rated iron loss? Okay, this type of questions. Iron loss variation is what? Approximately square of supply voltage. And copper loss vary with current. And how it will vary? What variation? Copper loss proportional to square of the current. Okay, copper loss proportional to square of the current. Iron loss approximately square of the supply voltage. Okay, so iron heated up, winding heated up. So due to that overall heat increases. If you don't reduce the heat, there is a chance of mainly copper winding will burn here. So we have to reduce that heat developed. For that, the oil is one of the cooling method we use, and if you see on the nameplate of this transformer also, you can able to see there type of cooling ONAN. type of cooling, they will mention as ONAN. What is ONAN? Oil natural, air natural. So oil will be there naturally in that, and outside air when contact to the surface of this tank, automatically little cooling will be provided due to outside air. Okay, so that is called oil natural, air natural cooling. And also we have gas, hydrogen gas cooling, or fan cooling, that like exhaust fans we use at the walls of this transformer tank, some fans to take the heat outside continuously at the side walls or bottom of the transformer tank. We use these fans for effective cooling. But normal distribution transformers not required all that. Normal air and that oil is enough. But if you go to higher level transformers in power transformers, like very high rating, 100 MVA, 10 MVA, 20 MVA, in that range MVA ratings, so there definitely we need a effective cooling, particularly high voltage. If you see, like power transformers belongs to higher voltage capacities. So that transformers required little more better cooling than these distribution transformers. Okay, next. It will provide cooling and insulation for outside body and these windings and core of the transformer. Now at the top of this transformer we have, conservator tank. In between the tank and conservator we have a Buchholz relay here. This is a conservator, and this oil is also connected to conservator up to some level, but not completely. Some air gap is still present in this. Some gap will be there. That is very important in conservator. So this is one of the question also in JEE. What is the need of that gap in the conservator? To allow the expansion of oil, sometimes oil will expand here. So when this oil level little bit expanded, whenever the temperatures increases or heat in transformer increases, so then oil levels increases. When oil levels increase, here gap, whenever gap is there, that gap is filled by that oil at that time. If there is no gap at all, then where is the chance to allow the expansion of oil? For that we use that gap in the conservator. Okay. Next, not only that, below this conservator we will have one breather like this. So breather also will be there here. This is breather, and this breather is filled with silica gel. This breather is filled with silica gel like this. Now what is the purpose of the conservator? Is to allow the expansion of oil level and contraction of oil level during expansion and contraction, suction process. Okay, and what is the breather purpose here? So this is our conservator. This is conservator and breather. What is the purpose of breather? Breather purpose. Breather. So through that breather only, transformers will take the air outside, and transformers will take inside the air through the breather only. Breather is very important. So when it is most important is, transformers also will take breathe in, and transformers will breathe out also. Breathe in and breathe out. So when transformers will breathe out, whenever temperatures increase, the oil level increases here, and whatever air is present here, that air will come outside through this breather only. So that is called breathe out process. Air will come outside here. So that is breathing out. Transformers will breathe out. That is not a problem for us. Problem is breathe in process. So when transformers will breathe in, whenever temperatures reduces here, oil also gets cooled little bit, then contraction will take place. Means oil level will reduce. Oil level reducing in the conservator means that is called suction process. Suction. Air will suck into the conservator. Now some air will enter into this, because when oil level is reducing, gap increases, air gap increase, means some air should come into that. Sucking process we call, suction process. Now during that suction process, air will go inside the conservator. So whenever air is moving inside the conservator, if the air is directly going inside the conservator without any breather process here, then outside air will have some pollutants like dust particles will be there, moisture content will be there, because outside air is not pure form of air, so that air directly enter into that. Then it will damage the properties of that oil. So definitely it will reduce the life of the transformer. That's why the main problem is here humidity. moisture content in the air. If moisture enters into the conservator directly, the oil property, dielectric strength and all insulating property, everything will reduce. Okay. For that reason, by using this breather here, when breather is present, the breather is completely filled with silica gel. Silica gel. Now during breathe-in process, what happens is the silica gel will absorb the moisture content present in the outside air first. The silica gel will absorb the moisture content present in the outside air. So as moisture content is absorbed by silica gel, now pure form of air will enter into the conservator. Like that we provide purity to the transformer. That is, whatever air is taking inside, it is just like filtered and it is moving inside now. Now there is no moisture in that and it will not damage any properties of oil and all. Like that we protect. Okay, so this breather is important. So breathing out is not a problem, but breathing in is a problem for us. But we have to place that breather in order to filter that or to absorb moisture content present in outside air. Okay, so during that breathe in process, breathe out process also, cooling is provided. How? When it is breathing out, that hot air will come outside. When it is breathing in means oil level little bit reduced during cooling of the transformer. When it is cooling in, air sucked into that conservator. So air is moving inside. So what is outside air temperature compared to inside air temperature? Less. That's why it is also providing cooling to transformer. This breathing process also will provide one of the cooling to transformer. Okay. Next, this transformer core and winding completely dipped in this transformer oil. And here these are the other parts of information and how these windings we take. Suppose let it is HV winding terminals and this is LV winding terminals. How to take that wires outside? Through bushings. So not actually like this. So here we have to use insulators. Like this, insulators will be there. Through that insulator we take the wires outside. Here will be there at the top. I am showing here. Like this, insulators will be there. So through that we will take the wires outside. We call it is bushings, HV bushings, LV bushings. Okay. Next, if you talk about mainly the transformer core and winding, let's see what are the important points. In the transformer core, in transformer core important is the type of material we choose. How power is transferring from one winding to other winding in transformer? By induction process or by through this magnetic core only. So if core is not having some important properties or good properties, the power transfer capacity also reduces. If you want to transfer most of the power from one winding to other winding, the core should have some important properties. What are the important properties? In order to transfer most of the power from one winding to other winding, we need some important properties of core. What are that? Yes. What are the? Yes. High permeability required. High permeability, low reluctance, and it should be a good ferromagnetic material. Like that, some important properties are there for transformer core. Now, which material is having all these properties? Is silicon steel. Silicon steel is having all the properties whatever is required for us, like high permeability, low reluctance, ferromagnetic material, and low iron loss. So all are there in silicon steel. But in normal silicon steel, the problem is we have in the material called grains. In the steel ferromagnetic materials, we have grains. That is, the shape of silicon steel we call BCC, body centered cubic structure. So each BCC we call one grain here. Like that, some lakhs of grains will be there in a small piece of material. Some lakhs of grains. And in normal silicon steel, these grains are non-oriented. These are non-oriented. Because of non-orientation, the reluctance of the steel slightly increases. because of non-oriented grains. That's why what we need to do is we need to provide orientation of that. So we need to convert non-orientation into oriented steel. For that we use one process. In order to make non-oriented steel into oriented steel, one process we use. What is that process? Cold rolling process. By using cold rolling process, the steel will become oriented and the resulted steel we call CRGO steel. So CRGO steel is also a silicon steel. CRGO also silicon steel. But what is difference? Normal silicon steel having non-oriented grains, which will increase little bit reluctance. But CRGO steel, as grains are oriented, the reluctance is very low for that. Still reduces. So if reluctance reduce, the flux magnitude in the materials will increase. So that is we required. That's why CRGO steel we use in transformer core. This is material. And what type of core we have to use? Solid or laminated? Yes, we always use laminated core. Why we laminated? Laminated core is used. Why we use laminated? To reduce eddy current loss. To reduce eddy current loss. Laminated core is used to reduce eddy current loss. Now, eddy currents and all, so that is a separate topic again, but I am not giving any explanation of eddy currents, how it is producing, how to reduce. How to reduce is directly one of the methods is by using laminated core. Okay. So with this laminated core, we can reduce the eddy current loss. So this is a type of core, laminated. And what type of magnetic circuit we have? How many types? This is one of the JEE conventional examination question also. Explain the types of magnetic circuits. So we have two types of magnetic circuits. Types of magnetic circuits. There are two types of magnetic circuits. What are that? Magnetic circuit, nothing but core. The core in transformer is two types, like you know well, core type transformer and shell type transformer. Two types we have, core type and shell type. So there are some important differences between these two magnetic circuits. So only some important points I will give here. See, in core type magnetic circuit and shell type, what is one important difference is placement of winding. In core, where winding is placed and where core will be there. So winding will be outside, core is inside. So in core type transformer, winding surrounds the core. Winding surrounds the core. But in shell type, core will surround the winding because core will be there outside, winding will be inside of that. Okay, in shell type, core surrounds the winding. Core surrounds the winding. This is in shell type. Like this, out of these two, in which type of magnetic circuit leakage flux is less? Core or shell? Yes. In shell type, we have less leakage flux. Shell type less leakage flux, and core type we have more leakage flux. So leakage is more in core, but leakage is less in shell. Like that, out of these two, which is suitable for high voltage application? Core is suitable for high voltage application, shell is suitable for low voltage applications. Shell is for low voltage. Okay, because in shell type, both the windings, LV winding, HV winding, both we place on the same middle limb. Same limb, both the windings are located. That's why many turns we cannot place, because if you want high voltage, we need to place so many turns on the middle limb itself, so that much area may not be available there. But if it is core type, LV winding, HV winding, we place on separate limbs, so there is so much space available to put more number of turns. So automatically number of turns increases means voltage rating also increases. So that is in core type. And out of these two, which is called series magnetic circuit, which is called parallel magnetic circuit. Core is called series magnetic circuit. This is series magnetic circuit. And shell is called parallel magnetic circuit. Shell is called parallel magnetic circuit. Okay. Now, whenever the core is laminated, suppose if you see the laminated core, this is the side view of laminated core. Front view you cannot see laminations. From side only we can see the laminations like this. From side view. So these are the laminations. So like this some laminations will be there. From side view only we can see the laminations. Now this vertical part of the core we called limb of the transformer is this, limb. So this is one limb, this is another limb. Two limbs will be there. And this horizontal part of transformer core we called yoke of transformer it is. This is yoke. Now generally where we put the windings? On the limb only, like this we put number of turns here. Here number of turns will be there, okay, and here. So windings are placed on the limb of the transformers. Now if you see this limb having some cross section. Let the two types of cross sections we use. One is square core cross section and stepped core cross section. So square core, this limb cross section, suppose if you cut like this, or if you cut like this, the some shape will be visible to you. The cross section of the limb is two types. One is square. This is square core cross section, and another one is stepped core. Stepped core is nothing but at the corner of this same square, you just create some steps, one or two steps let us create. At all the corners create steps. That is called stepped core or cruciform core we call it is. This is square core. Now this is having some area, no? What is the shape of this? Square. As it is square core cross section, limb cross section it is. So here we define one important term called stacking factor. Important it is. One important term we define here is stacking factor. This is indicated with Ks. So what is stacking factor is? It is the ratio of net cross-sectional area of core to the gross cross-sectional area of core. Net cross-sectional area of core to gross, because this is a laminated core, no? Laminated core. So what will be there between each lamination? See, these are all insulating materials. Oxide paint coating or varnish paints will be there. Paint coating, this is insulation. This is iron, and in between insulation is there. So in between these two laminations there is no conduction. There is no direct conduction. Electrical conduction is not there. These two are isolated with insulation here. So if you find the area of this using the formula, let each side is having some magnitude x. Each side is some x centimeter. All are same because square it is, all sides are equal. Then what is area of this square? Area. Formula is what? If you find area from this x square, area formula is side square only, x square. So using this formula you will get gross area. Gross it is. Gross means it is the area occupied by both the iron material and insulating material also included in that. That is called gross area. And if you find net area, what is the net area is? Net area is nothing but area due to only iron material. So if you remove that insulation in between, whatever is there, we get the net area there, only iron material. So that ratio, net area to gross area, we call stacking factor. But directly you cannot find net area. They should give some stacking factor. Then only you can find that net area how much. Otherwise we cannot find directly net. Gross you will get from formula directly. So if you want to find net area, stacking factor important. So stacking factor they give some 90%, 92%, 94%, 95%, anything. Suppose 95% stacking factor given. That means what? If stacking factor is 95%, means 95% is iron and remaining 5% is what? Insulation in between the material, in between the laminations. 5% of insulation is there. Okay. Suppose stacking factor equal to 1, that means solid core it is, no laminations. Stacking factor equal to 1 indicates solid core. Remember this. For laminated core it is always less than 1. For laminated core, stacking factor always less than 1 will be there. 98, 97, 96, whatever it is. Only for solid core, solid means no insulation, net, gross both are same there, then Ks equal to 1. Ks equal to 1 for solid, less than 1 for laminated. Okay. So these are some important top points in transformer core construction. Next, in transformer winding construction, what are the important? Tell me. Transformer winding, important is only one thing, that is placement of winding. So only one important topic in transformer winding is placement. Second one, transformer winding. Transformer winding. Just important points I am writing here, see this. So in the transformer winding, we have two windings, LV winding, HV winding. Now which winding first we prefer to place on the core, which is advantage. So always we prefer to place LV winding because if you see, for example, this is the limb of the transformer. This is limb. So here we place winding. So we put whether it is core type, whether it is shell type, we prefer to place both the windings. Suppose if it is core type transformer, the winding used is called core type. In core type transformer, the winding used is called concentric winding. Concentric and interleave winding procedure. Concentric and interleave winding procedure. And in shell type transformer, the winding procedure used is called sandwich winding procedure. Sandwich winding procedure. Now, why we use both? Why we use the first one concentric and interleave? Why we use sandwich? Every reason is for both to reduce leakage flux. To reduce leakage flux in transformer, we use these windings in the particular type of magnetic circuit. Concentric nothing but 50-50. 50-50, that is, if it is the limb of the transformer, half LV winding, half HV winding we place on this side, and other side also half LV winding, half HV winding we place. So we don't place complete LV winding one side, complete HV winding one side. With that, leakage increase. If you put half LV, half HV one side and remaining half LV, half HV other side, leakage flux will reduce mainly. And in sandwich also same. So shell type transformer, anyhow both the windings are same limb, middle limb only we place both windings. And in that still we divide into some number of parts, layer by layer we put the winding, LV insulation, HV insulation, LV insulation, like that we put. Just like sandwich arrangement, layer by layer we place. No? Same way we put the winding in case of shell type, that's why we call it a sandwich type of winding. Why we put like that layer by layer again is, again to reduce leakage flux. In layer by layer arrangement of this LV, HV, windings will be very near to each other. Then if windings are very near to each other, leakage flux will reduce. Because distance should be less between the windings to reduce the leakage flux. Now, which winding is preferred to place near to core first or on the core first? Always we preferred LV winding first on the core. LV winding is preferred to place first on the core. First on core, and on that again insulation, on that HV winding we put. First LV winding and then HV winding. Now what are the advantages of placing like this is, the main advantage is insulation required reduces. Insulation, because between the limb and in winding some insulation required, again winding to winding insulation required. The insulation required will be reduces if you put LV winding. Okay, whenever insulation reduces, diameter reduces. Insulation reduce means thickness reduce. Then when you put copper wire for each turn, as diameter is reduced, copper wire requirement also reduces. So copper requirement reduces, and due to this size and cost of transformer reduce. Size and cost reduces. And one more is leakage flux. Leakage flux also reduces, because whenever LV is placed first, insulation required between core and winding is very less. Suppose if you put HV winding on the core first, so much insulation you have to put first and then winding on that. If insulation increase, the distance between core and winding also increase. But insulation reduces, no? Whenever we place LV winding, winding will come very near to core. That's why leakage will reduce here. So windings always should be near to core, and two windings should be near to near again. Then leakage will reduce. So leakage flux reduces. And other advantages is tappings. If you put LV winding, first on the core, which winding will come outside? HV will come outside. Now generally tappings we provide on the transformers. So tappings provided on which side of winding? Which winding? HV winding we provide. Because HV side we have so much voltage range, HV side current rating is less. So whenever we tap, sparks will get less because of low current in HV winding. So due to these advantages, we always do tappings on HV winding only. Which winding? Outside. HV, na? That's why easily we can tap the winding. But if you put HV winding inside first, tappings is difficult to provide. That's why. So these are all some advantages of providing LV winding first on the core or near to core. Over that HV winding we place. So this is important in placement of winding. Okay. Now let's see some important questions related to this transformer. See the question. A transformer has maximum efficiency at full load when iron losses are 800 watts, copper losses at half load will be dash. A transformer has maximum efficiency at full load. Then what is the copper loss at half load? How much? Answer. Tell me the answer. How much it is? Yes, it is 200 watts. 200 watts is the answer. Simple question. $200 is the answer. Why? Maximum efficiency at full load given. So at maximum efficiency condition is what? At maximum efficiency always copper loss at maximum efficiency condition is copper loss equals to iron loss. What is the iron loss given? 800 watts. Iron loss is 800. So this is the copper loss 800 watts. At what condition? At full load condition given. Maximum efficiency condition is copper equal to iron. At where it is maximum? Full load. So full load copper loss given directly. Now question is copper loss at half full load is dash. What is the formula for copper loss at any fraction? Half, no? 1 by 2 whole square. Suppose if it is 70%, 0.7 square like that. 1 by 2 whole square into full load copper loss. 800. This is 1 by 4 into 800. Nothing but 200 watts. So this is the copper loss at half full load. 200. Next question. See this question. The efficiency of a 100 kVA transformer is 0.98 at full load as well as half load. For this transformer, at full load, the copper loss is dash, equal to less than core loss, equal to core loss, more than core loss, all the above. What is the answer? What is the answer? How much it is? Given that efficiency is some 98% at full load as well as half full load. For this condition, what is the relation between copper loss? Yes, option C, it is more than core loss. Why? Because if you draw the variation of efficiency with current, like this we get efficiency with current. So whenever current increases, Whenever current increase, efficiency also increase. Here given that the efficiency is 98% at full load. Let this is no load point, zero current, and this is rated current, or assume full load current, it is full load. At half full load and also at full load, the efficiency is 98%. Okay, that means maximum efficiency will come in between the 2 points, somewhere, some 70% or 80% or 75%, somewhere maximum efficiency we have. This is the maximum efficiency. Okay, now at maximum efficiency, what is the condition here? Copper loss equals to iron loss. That is the condition for maximum efficiency. But where they are asking for this transformer, the at full load condition copper loss is dash. Full load means here. At this point both equal. So at this maximum efficiency both are equal. For now further current increases. Iron loss will never increase, never change, constant, no it is. So as current further increasing here, copper loss only increases. Now at this full load condition, which loss is greater? So at full load, copper loss is greater than iron loss or core loss. Copper loss is greater than iron loss or core loss. So more than core loss. Option C is correct. Next question. See this question. If a 500 kVA 200 volt 200 hertz 500 kVA 200 hertz transformer is operated at 50 hertz, then kVA rating will be dash. Tell the answer. Answer is dash. A 500 kVA 200 hertz transformer, actually now it is operating at 50 hertz only. Then what will be its kVA rating? Answer. So definitely reduced. See, 200 reduces to 50 hertz means almost 1/4. kVA also 1/4. So 500 kVA initially. Now what is 1/4 of that 500? 125. So 125 is the answer. 125, because kVA rating is what mainly? kVA rating is the product of voltage and current, okay, proportional to voltage and current, and this voltage or EMF of windings or transformers proportional to, in the equation we have 4.44 phi f t or phi f n, number of turns. So EMF is proportional to frequency here. Whenever it is operating at 200 hertz, EMF will be more, then we get 500 kVA. Now frequency reduced to 1/4, EMF also reduced. So whenever EMF reduced, kVA rating also reduced. So it is 1/4, okay. That is 125 kVA we get. Clear? Next question. Next. See this question. In case of a power transformer, the no load current in terms of rated current is dash. So what is the percentage of no load current? See, this percentage is important. No load current, magnetizing current, iron loss current, percentage is important for every examination. So what is the percentage of no load current in terms of rated current? Answer this. What is the answer? So don't forget these percentages in transformer and induction motor, they are related almost. The percentage of no load current is 3 to 5%. Very low it is. Mostly up to 5% will be there, not more than that. If it is a induction motor, you may have little more, 15 to 30% like this will be there for induction motor. But for transformer, no load current is almost around 5 to 6% will be there, not more than that. So out of the given options, lowest percentage is only this 3 to 5. Okay. And this is no load current. No load current is the sum of what? Two currents again, magnetizing current and iron loss current, IW. What is the percentage of I mu? So it is approximately, remember, 2 to 4%. and IW is 1 to 2 percentage. Very small it is. IW percentage is less. IW 1 to 2 only. I mu 2 to 4% and I naught approximately 4 to 5 percentage will be there in this range. This is the percentage of no load current, magnetizing current, iron loss current. If it is induction motor, I mu percentage is very high, approximately 25 to 30 percentage. IW little increase, 2 to 5% like that, IW. And overall I naught will be in the range approximately 30 percentage of full load current or rated current. So that is more in induction motor, less in transformer. Remember this. Next question. See this. A three-phase transformer has its primary connected in delta and secondary connected in star. Okay, delta star transformer it is. Secondary to primary turns ratio per phase. Secondary to primary turns ratio per phase is 6. For a primary voltage of 200 volts, the secondary voltage would be dash. Calculate this. For a primary voltage of 200, the secondary voltage is dash. Find out this. Find out what is the secondary voltage. Primary voltage given 200 volts. What is the secondary voltage? What is the answer? How much? No answer. Simple one. You have to find out three-phase calculation important. So easy question, small question only in three-phase. No one? Primary voltage given 200 and this given voltage what we need to consider, line or phase, nothing is given, so line voltage it is. This is line voltage. So primary connection is delta. What is the phase voltage in delta? Also same, line voltage only. So primary phase voltage or line voltage is primary phase voltage. Also same 200 volts because delta connection it is. Now according to this turns ratio relation, we have secondary phase voltage to the primary phase voltage. E2 phase by E1 phase is N2 phase by N1 phase. That ratio they given N2 by N1 is 6. Now what is the secondary phase voltage from this? 6 into 200, nothing but 1200 volts. So here there is 1200. If you put 1200, that is also wrong. It is not 1200. Why? Because you need to say the answer again line only. They given line, you should give the line voltage answer. Secondary connection is what? Star. In a star connection, line voltage is √3 times of phase voltage. So the line voltage on secondary is √3 times of phase voltage. So if you calculate, we get 2078. 2078. Or more than 1200, only one option is there. Like that you can put option A, it is 2078. Okay. (2078 volts). Clear? Take care whether the connection is delta delta or star star or star delta or delta star. So based on the connection you need to answer this phase voltage, line voltages. Unless otherwise specifically given, always the given voltage in three phase is line voltage only. If particularly mentioned primary phase voltage, then only take it as phase voltage. Next. Next question. Low voltage windings are placed nearer to the core in case of concentric windings because of dash. LV windings we place near to core. Okay, what happened with this? Because of this, what will happen? It reduces hysteresis loss. So why we put mainly that LV winding near to core? Due to some advantages. What is that? It reduces hysteresis loss? No. It reduces eddy current loss? No. It reduces insulation requirement? Yes. It reduces leakage flux? Yes. This is also correct. Now if it is MSQ type, that is multiple select question, then both will be the answer. Now which one we have to choose? C or D? Which one? Yes, now we have to choose C only, because mainly by placing LV winding near to core, insulation requirement will reduce there. With that remaining leakage flux, everything will reduce. First here preferable is insulation will reduce. Leakage flux also reduce, but whenever insulation reduce, then only this one will reduce. Otherwise if insulation is not reduced, no, then distance will be more, leakage will not reduce. That's why first preference is insulation will reduce mainly. Okay, next question. See this question. The load carried by VV connection is dash. The load carried by VV connection is dash. What is the answer? Load carried by VV connection. VV connection nothing but open delta connection. Okay. Load carried by VV connection is dash. Tell me directly, yes. What is the KVA rating of open delta? KVA rating of open delta is equal to how much? 0.577 or 1 by root 3 times it is 0.577 into KVA rating of delta delta. Delta delta is original connection. Now whenever one of the phase gets fault or damaged or fault takes place, then it becomes open delta. So open delta can able to still supply balanced 3 phase with reduced capacity. Now open delta can supply how much? 57.7% of delta delta only. Okay, 57.7%, option B. It can supply 57.7%. Next question. How can the magnetic flux lines in the magnetic circuit shown be increased? How can we increase flux in the core? How to increase flux? From the options. Flux is equal to magnitude of MMF divided by reluctance. How can we increase the flux lines in the core? By decreasing magnetomotive force, that is by decreasing MMF? No. By increasing MMF, by making air gap in the core. If you make air gap, reluctance further increase. If reluctance increase, flux decreases automatically. So that is not correct. So this is not correct. By reversing direction of current, if you reverse the direction of current, same magnitude of flux will be there, but in opposite direction it will flow. So this is also not correct. So first one is also wrong, second one is right. By increasing MMF of the winding, by increasing MMF. Okay, right, 57. See this question, this is important, try to answer this. A single phase transformer is connected as shown in below figure when a voltage of 100 volts applied, 100 volts applied here. When a voltage of 100 volts applied across AB, the voltmeter connected across AC, this is the voltmeter connected, here it measures 100 volts. That means what is the turns ratio N1 is to N2. So in polarity test we get this figure. There you can understand we have some of the voltmeter may read some of the voltages of primary secondary, it may read difference of primary secondary. So anyhow volts applied, this voltmeter reading 100 volts. That means turns ratio is how much? Answer this. Turns ratio how much? See, 1 is to 4, no. The voltmeter may read sum of the primary secondary or difference of the primary secondary. So that is not given. So you have to understand based on the turns ratio given in options. Suppose if you choose 1:2, no? Choose the first option 1:2 means 1:2 means 100 volts applied, no? Here 200 volts will come. That is 1:2. Now if the voltmeter reads sum, it should get 300, but it is not showing, and difference of the two is what? 100 volts. So it is showing 100 volts here. So it is accepting, it is correct. If you take 2:1, if it is 100 volts, here 50 volts will come. 2:1 means what? Here 2 turns, here 1 turn. For 2 turns voltage 100 means 1 turn is 50. Then here 100, here 50 means you never get 100 minus 50 is 50, 100 plus 50 is 150. You never get 100. So only one option will satisfy here, that is 1:2. Okay, like that we have to check it is from options. 1:2, 100 applied means here 200 will come. Then when you take difference, 100 is coming. Yes, it is right. Difference, voltmeter reading difference here, that means. Okay, that is only the possibility. Okay, clear? Option A is correct. 1:2 number of turns ratio. See this? Completed this? See this question. Read the question regarding Scott connection. Scott connection is used for dash. Scott connection is used for dash. Single phase to three phase transformation, three phase to single phase, three phase to two phase transformation. What is the main purpose of Scott connection? Tell the answer for this. Scott connection main purpose. Yes, Scott connection we used either to convert available three phase into two phase or available two phase into three phase. Okay, it is three phase to two phase conversion always. So three phase to two phase transformation. Option C is correct. Right. Three phase to two phase it is. Okay. So these are the questions for today in the transformer topic. Okay. So try to practice the previous questions as much as possible for RRB JE examination. Okay. All the best.